Hi, my name's Phil Lewis, and I've put together some slides on the activities and content in the building models section. So the section starts with a discussion of the modelling process. Everyone's got a different take on what that might involve, but here my take on it is that we try and model a biological system by taking together our experimental observations and the knowledge we already have of what biological processes are involved, and we try and formulate those things into a mathematical model which can reproduce the observed behaviour with while being constructed in such a way that it's consistent with what we know about the biological processes. And when we have a model that we're happy with or can't develop further, we try to use that model to generate the next set of experiments. So whether it's measuring some of the rates that are going into our model, or whether it's testing whether a certain behavior that our model shows given certain inputs, if that's reproduced in the experimental system, or maybe it's that the model predicts if we interfere with some of the reactions, like inhibit some of the pathways, we'll have a certain kind of behavior, and we could find, if we find that, the same thing experimentally. So we might get new ideas for our experiments, or it might be we get some clues as to the underlying biological processes. It might be that in our model we find that only certain processes seem to dominate the behavior of the system, so maybe a clue that towards which processes are important, or it might be that without including some new process or new reactions, we can't explain the experimental results, and we have to go away and try and think about what other processes might be taking place. So that's given us new sets of experiments to carry out, more ideas to research, and once we've done that, we hopefully can go back and improve our mathematical model. So the aim of this topic is really looking at that first step. How do we go from where we've just got a graph of experimental results and a little bit of information about the biological processes in the system, and take that and actually formulate that mathematical model? So it's taking that first step. So for instance, if we have an experiment where we've introduced substance X into a system and we have an observable, given different behaviours that we find, such as moving from one steady state to a different steady state, or maybe a sort of peak-like response, or maybe an oscillator, a response which oscillates, how do we actually start to think about what the system might look like and make a mathematical model for that system? So what we're going to do is firstly put together the different rate equations for various processes. So we've seen previously in this topic different types of rate equations for different types of reactions. We're just going to draw, we're going to build up a toolkit of those of the reactions we're going to use when we're building our models. So in our modelling toolkit there's going to be 5 processes. The first process is where we just add something, so a stock, into a constant rate into our experiment, so it's a constant flow. In this case, the rate of change of that substrate is just going to be constant because it's a constant flow. And if we have a high value for K, that corresponds to a high flow of S into our system. So that's process 1. Process 2 is an actual reaction, so substrate X is being converted into product P. So from a law of mass action, we might expect that the rate of this reaction is proportional to the amount of substrate we have present. So if we double the amount of substrate, we expect to generate double the amount of product in any given time. So double the rate at which P is formed. And if we transform that relationship of proportionality into an equation, this is what we get, where we have a constant of proportionality K. So just before we move on to the next process, there are certain situations in which we can simplify that equation. So consider the following two cases. The one we might have generally is that our substrate gets used up over the time course of the experiment, so the concentration falls. That's what we might expect. But it might be that, say we have a large reservoir of a substrate in our environment, or the rate is very slow, or it could be that we're replenishing or drawing on the substrate from some in the outside environment, so it's held constant by that. So what we're saying here is there is experimental cases where the concentration of a substrate is approximately constant with respect to the time period of our that we're observing the system over. And in this case, because the rate is proportional to the amount of substrate, in the first case we'd have a significant change in our rate, but in the second case, where our substrate is remaining approximately constant, then the rate of the reaction is also going to stay approximately constant. So if the level of substrate remains approximately constant in the system, then we can simplify and approximate the rate of substrate converted to product to be a constant rate. So that means, so that simplifies to this equation where the new constant is related to the original reaction rate times this constant concentration of the substrate. Okay, so that's a simplification for that process. The next process is where we have a reaction between two different substrates to form a product. So now the law of mass action tells us that the rate will be proportional to the concentration of substrate 1 times the concentration of substrate 2. So doubling the concentration of either substrate will double the reaction rate. If we doubled both of them at the same time, that would quadruple the reaction rate. And so in the same way we have this differential equation to define the rate of this reaction. So we've looked so far at mass action type equations. Now we're going to say, well, there are other types of equations where we're not looking necessarily at reactants involved in the reactions, but we're looking at things that do affect the rate of them. So for instance, enzymes affect the rate of a reaction without being a reactant or product. And we might say the presence of an enzyme activates a reaction. So we're looking at activation where the reaction rate increases as concentration of some activator A increases in the system. So I've used this notation where above the reaction arrow I say A plus to show that the presence of A is increasing that reaction rate. So if we think how we can model this with a simple, with a simple expression, well, we could just say, well, let's set the rate of the equation to be proportional to the amount of activator present. So doubling the amount of activator doubles the reaction rate. So this is the equation we'd use for that. So in this model, doubling the level of A will double the reaction rate, and in the absence of A, when the concentration of A is 0, the reaction rate is 0. So that's one way to model activation. However, suppose experimentally we find that the reaction rate isn't zero and the reaction is still proceeding in the absence of our activator. Well, we could modify this equation to include a baseline rate by writing it in this form. Now we have two different constants, and when the concentration of A is 0, we have a rate is equal to K0 times the concentration of our substrate. So K0 represents a baseline rate, and then we have this extra constant Ka, so that determines the strength of activation by the activator relative to the baseline reaction rate. So if we have activation where there's a baseline rate in the absence of our activator, we can use this equation. There's another case or another modification we might want to look at now. Suppose experimentally we find that when we double the amount of A in a system, the reaction rate actually more than doubles. How could we model that? Well, if you remember the Hill equation, we could say, well, let's try setting the rate to be proportional to the amount of A present raised to the power of n, and we will let n vary from 0 up to whatever number we like. So our equation modifies to this, and in the case that n is greater than 1, doubling the amount of A is going to more than double the reaction rate. In the case that n is less than 1, then doubling the amount of activator will still increase our reaction rate, but by less than double. So by incorporating this power of n in our expression, we have more freedom to fit our experimental data. And it may have physical meaning. So for example, if n equals 2 gives our good fit to the experiment, i.e. the differential rate for that process is given by Ks times A squared. The rate is now proportional to the amount of activator squared, and that could indicate that substance A must form dimers before it can activate the reaction, so it might have a physical meaning. Okay, so the final thing we're going to talk about activation is modeling activation where you have saturation of the reaction rate. So that's a bit of a tongue twister. But we've already seen the Michelson-Menten and Hill equations, which have this idea of reaction rate saturating at a maximum. So once you've added a certain amount of enzyme, the reaction rate saturates. So initially, as you increase the amount of activator, the reaction rate increases, but eventually it reaches a maximum and stays constant as you increase the amount of A even further. So just comparing between the Michaelis-Menten and Hill equation models where you have saturation and our simple model where the reaction rate is proportional to the amount of activator you have present. So in our simple model, every time you increase the amount of activator, you increase the reaction rate. But say for the Michaelis-Menten model, what you find is initially that's the case, but as you increase A further, eventually it saturates, it flattens and reaches a maximum rate. So the thing I want to draw your attention to is that the initial behaviour for small concentrations of A for both models is the same. So we can use our simple model for the process reaction rate as long as our level of activator stays well below any saturation level. So this is a justification for why we can use our simple model rather than like the full Hill equation or Michaelis-Menten form. So that was activation. We'll now come to its counterpart, inhibition. So that's where we have a reaction rate that decreases as we increase the amount of an inhibitor I present. So here's my notation where I say inhibitor I is negatively affecting the reaction rate. So I put a negative symbol in a circle. And in order to model it, we can try a similar approach as we did with activations. So before we had the rate was proportional to the level of activator. So we could say, well, it's reasonable to try setting the rate to be inversely proportional, so that doubling the amount of inhibitor present halves the reaction rate. So this does model an inhibition effect, but the problem is in the absence of our inhibitor, so the concentration is 0, it predicts the rate will be infinitely large because you have 1 divided by 0, so it's not physical or realistic. And from common sense, we know in the absence of our inhibitor we'd have a baseline rate, and then as we added more of our inhibitor into the system, or as we introduced our inhibitor and then added more, that rate would reduce. So we can model that relationship with this formula. So we've got divided by 1 plus Ki times I, where now when I is 0, when we don't have inhibitor present, that expression reduces to just K naught S. So that's saying that K naught S or K naught is now a baseline rate for that reaction, and Ki is a constant that determines the strength of inhibition compared to that baseline rate. So the higher the value of Ki, the more effective your inhibitor is at slowing the reaction rate. So again, just say we have a model of an inhibition for a system and we match it with experimental data and it doesn't quite match that form. How can we modify that expression? Well, just like we added a power of n in our activator concentration, we can do the same with our inhibitor. So if we feel the need to, in order to get better agreement with our experimentally measured system, we might try allowing for a factor of n in our expression to the rate. And now if you compare that to the case when n equals 1, so that was our default or the most simple expression, when n is greater than 1, the inhibition is stronger when you have larger concentrations of the inhibitor present, or when if you have an n value that is less than 1, your inhibition still takes place, but less strongly as you increase the amount of inhibitor present. So it has a less strong effect when n is below 1. So that completes our toolkit. We've got an equation for constant flow of something into our system. We've got an equation for when a substrate just converts into a product. We've got an equation for when two substrates react together to form a product. We've got a simple model for activation and a simple model for inhibition. So those are our 5 expressions, and we've also talked about modifications to those expressions, which might be ways to either simplify them or match them to different experimental situations. So the next thing to do now we've got our toolkit is apply those what we've gathered together to an example. The example we're going to look at is the EPO signaling cascade. So erythropoietin, or EPO, is a hormone that controls red blood cell production, and it binds to receptors on the surface of red cell precursors, and it activates red blood cell production. So the signaling cascade begins with phosphorylation of the EPO receptor. So this is my diagram. We have our EPO receptors on the on the surface of the cell. EPO is present, it binds to the receptor, and that kicks off a chain of reactions starting with phosphorylation of the receptor, and then that leads to a signaling cascade of other processes. So the question we're asked is, how does the level of phosphorylation of those receptors change in response to the introduction of EPO into the system? So here's a step change in the level of EPO. So initially EPO is absent, we add it in. Do we get some kind of permanent activation? So we get the receptors permanently phosphorylated as long as EPO is present? Or is there some process by which it means there's just a temporary activation of that signal, and after a short while the phosphorylation is lost and they just the processes initiated by EPO being present end? Or is it some sort of oscillatory activation? So there's different kinds of behavior possible, and we want to find out what the behavior is and then build a model for it. So we start off by looking at the experimental data. So the paper that's suggested in the textbook is Schilling et al. And what they did was they actually show how they construct quite a complex system or a complex model for the EPO receptors and the chain of reactions that they control. But in this example, all we're going to do is look at the level of phosphorylation of the receptors. So I've pulled out that experimental data. Now you'll see it's not quite the same data as is used in the textbook, and I've used this one because it actually shows the error bars, and it gives us a better idea of what possible models are acceptable to fit the data, because we can see the error bars. We see a bit more that the measurements are actually quite noisy. There's quite a bit of leeway particularly in the earlier measurements on this system. So at time t equals 0, they introduced EPO and then measured what percentage of receptors were phosphorylated, and that's what you're looking at there. So just observations, what is that showing us? Well, initially we get a sharp rise in the level of phosphorylation from 0 to about 50% after 2 minutes. And what we see is the measurements fluctuate quite a lot, but it's clear, or it seems that that level of phosphorylation, there's significant phosphorylation until about 20 minutes. So it's hard to say whether it's starting to fall or it's constant, but what I would say is there's significant phosphorylation, but that after about 20 minutes that level has dropped down to about 10%, and it remains at that level for the rest of the experimental reading, so up to about 70 minutes at least. What biological knowledge have we got to go with that experimental result? Well, just simply we know that phosphorylation of the EPO receptors is activated by the presence of EPO, and we can compare that with a reaction in our toolkit, the activation reaction. And we also know there must be a backwards reaction, dephosphorylation, and so that's just phosphorylated EPO receptor goes to unphosphorylated EPO receptor, and we might compare that just to the straight substrate to product reaction in our toolkit. So just to be clear, at the moment we're writing down some of this, the simplest reactions, and we're just going to test what happens in our model, and we're fully expecting that we might have to add in more things and make it more complex if we're going to match our experimental data. So we've got our processes we're going to start off with, and we need to code that and simulate it in MATLAB. So the processes we have are phosphorylation, that's process 1, and dephosphorylation, process 2. And we've got those, we can match those with our toolkit processes to write down the rate equations to those two processes. In our MATLAB code though, we need to model the rate of change for each species, not just a process. So we need to write down the rate of change of unphosphorylated EPO receptor and the rate of change of phosphorylated EPO receptor. And here I've just written them in terms of the processes. And then after I've done that, I can replace that with the exact expressions that we've got on the previous page. Okay, so what assumptions are in that model? First of all, we're assuming that we can reproduce the system's behavior by only dealing with those three species, so the EPO hormone, then the EPO receptor, then the phosphorylated EPO receptor. Secondly, we've modeled the activation as a sort of proportional relationship. So that means in our model, when EPO is absent, there would be no phosphorylation reaction, and that phosphorylation reaction never saturates, it never reaches a maximum rate. So as you increase the amount of EPO, you're assuming that the reaction would always increase. Or that's built into our model. And the third assumption is that the receptors only undergo phosphorylation and dephosphorylation, so the total number of receptors is conserved. We don't have production or destruction of those receptors. And similarly for EPO, it doesn't degrade, or there's no processes which are creating it or destroying it over the course of our experiment. So you might, having made those assumptions, some of those might be testable experimentally. So in addition to measuring the level of phosphorylated EPO receptors, you could also model the amount of EPO in your system, and that would be a way of testing assumption 4. Okay, so we've got our equations for the different rates. Let's code those up. So we start off by defining our function file. So I've called my function ODE EPO version 1, and the inputs to that are the current time, the current concentrations of all the species involved, and then a parameters object. And that parameters object is going to take anything you want to, is going to take the parameters for our reaction, so the reaction rates, the concentration of EPO, and also the time at which EPO is introduced to the system. So the first thing I'm doing is taking that vector P and converting the values in it to named variables. So that's going to make it easy when I'm writing my equations to know exactly what I'm referring to. And the same thing for the species vector. I convert y1 and y2 into names that represent the species that they're storing. So unphosphorylated EPO receptor and phosphorylated EPO receptor. And now everything's got a name, I can start my code. So the first thing I need to do is work out whether, given the time I'm at, time t, if it's before t EPO, then that's before I've introduced EPO into the system, so EPO needs to be set to 0. If it's not before the time I introduced it, it must be after, and therefore the EPO gets set to the concentration of EPO I've added. Now I can work out the rates of the processes. So I've got the The first line is the rate of phosphorylation. The second line is the rate for dephosphorylation. And with those two rates, or using those results, I can write down the rates of my species. So the rate of change of unphosphorylated EPO receptors and the rate of change for my phosphorylated EPO receptors. And they're just according to the results that we've had previously. So I write those back into my results vector dy, and that's the end of my function file. To run the simulation, I need a script file. The first thing I'll do is define all those parameters, give them values. So concentration of EPO I've defined as 1. The time EPO is introduced I've defined as 2. The rate parameters K1 and K2, I've just set those to 1. And the idea is just to put in some test parameters here, and then when it comes to, once we've had a quick look at how the model behaves, what the parameters control, we can then try and change those and match them to our data. So I have a line now which runs a simulation and stores the results in my T species vector. So what I'm passing to the ODE45 is first a function handle, so that's the ampersand, then the function name. Then I pass my time limits, so I'm simulating the system between 0 and 10 time units. Then I pass my initial conditions, so initially the level of unphosphorylated EPO receptors is 1, the level of phosphorylated EPO receptors is 0. That's because I haven't got any EPO in my system, so everything starts off unphosphorylated. Then I pass this ODE set parameter, and after that a vector, the parameters vector P, and that passes those parameters to the function. So after that line I've got my results. I create a new figure and I plot the results, and if you reproduce those files, this should be what you see, that at time 2 when EPO was produced, the phosphorylated receptor level rises and then reaches a steady state of 50% and continues to stay at that state. So the tasks I have for you is write those code files yourself and then repeat the simulation but with different values for the rate constants, because what I want you to do is be able to describe how the values of K1 and K2 affect the model. Okay, so what I'm going to do now is just evaluate that model and try and think of what the next step is. How can we modify it to better match the results? So I'm just thinking qualitatively, like how is the behavior of my model matched the behavior of the experimental data. So we see the level of phosphorylated receptor rises as EPO is introduced, so that's correct. So in the experiment EPO was introduced at time 0 and the level rose. In the model it was introduced at time 2 and it rose, so that's in agreement. Then we see the level of phosphorylated receptors in the experiment decreasing to a lower level. We don't see that in our model. And the final thing I'll mention, that in the long term there's a steady level of phosphorylated receptors, and you might argue that our model also has that behavior, but it's debatable because it's not dropped. Could you really say it stays at a long steady state? So you might disagree with me on that. But what we need to do next is a way to make the level of phosphorylated receptor fall as the system evolves. So after that initial rise, we want it then to fall. So we could make the level of phosphorylated EPO receptors fall by decreasing that forward phosphorylation rate, or increasing the dephosphorylation rate, the backwards reaction. So one way to do this could be that if a downstream product of that signaling cascade is an inhibitor to the phosphorylation, the forward reaction, then what would happen is we add EPO, the receptors become phosphorylized, the signaling cascade kicks off, we get this product of that cascade which then builds up and inhibits that phosphorylation, so the amount of phosphorylated receptors starts to fall. So our processes now are production of some species X, we're going to call it, that is activated by the presence of phosphorylated receptors, and then we're going to modify our process 1, so as well as being activated by EPO, it's going to be inhibited by the presence of X. So now we can code that model. So our processes are modified. So now process 1 has the inhibition by X factor. Process 2 is unchanged, and we need to add a new process for the production of X. So modifying our rate equation to add in the inhibition by X, we get this form. Our second process stays the same, and our third process, that shouldn't be a minus sign in there, that's just something that needs rubbing out. So our rate should be equal to a constant times the amount of phosphorylated EPO receptor present. And what you see there is we're not including anything else that might affect the rate of production of X. So we're assuming that we can ignore anything apart from the phosphorylated receptors having effect on the rate of production of X. So we've got our processes and rate equations for those. We need rate equations for each species involved. So rate equation for EPOR is the same, and the same relationship for phosphorylated EPOR. But now we've got this species equation for X we've got to involve too. So in terms of those three processes, we can write the change in the species as -1 plus process 2, process 2 minus process, Okay, so there are species equations written in terms of those processes, and we can just substitute in the rate equations we found for those processes. So the additional assumptions here are that our inhibitor X is produced in a reaction activated by EPOR, and that activation is proportional. 2, that the inhibition of X on the phosphorylation can be modelled by the form in our toolkit. And the third one might be that X does not degrade. So X is just building up in the system, there's no way for it to degrade, to be removed at present. So our function file, I've called it ODE EPO version 2 to reflect it's a modified function. We have extra parameters K3 and K4. We have extra species X, but then it proceeds pretty much as before. We just set the EPO level according to whether it's before or after the time we injected it. We write our rate equations according to the rates we had on the last slide, and then using those rate equations for the processes, we write the rate equations for the species, and finally we write the results back into a results vector dy to pass back to the ODE solver. Okay, so that's our modified function file. Our modified script file looks like this. So we have 2 extra rates that we have to have values for, K3 and K4, Again, to start with, I'm just going to set those to the value of 1. And we run the simulation in the same way. You'll see I've increased the time period for which I'm simulating, so we get the full, we can see more of the behaviour. And also we have an extra species for the initial conditions. So now the initial conditions read 1, 0, 0, and that final 0 refers to the fact that we start off with 0x in our signal, in our system. And again, with the parameters p now includes k3 and k4. So we create a figure and plot the results as before, and this is our output plot. So just some tasks. Try and vary the values of k3 and k4 as you did with k1 and k2, and describe how they change the behaviour if added. Yes. After it's risen, the level of phosphorylated receptors falls to a lower level. Yes. And in the long term, the system drops to a steady level. Yes. So our modified model now can be made through choice of K1, K2, K3 and K4 to agree with the data within the experimental errors. So you might say that's a success. So I've just got a couple of remarks on what we've done. So the first one, if you go in and read the original paper, you'll find that the behaviour they predict for the phosphorylated receptors is slightly different. So they predict that the level rises, is sustained, and then falls, compared to our model, which suggests we have a rise, peak, and then fall. So it's slightly different behaviour, and the thing I might want to ask is, are both consistent with the data that they found? And then maybe if you look at the paper, you can try and understand why their model is different. Our second remark, this is the fact that our model is based on the following 3 processes, but there are other ways to get the same kind of behaviour and match the experimental data. For instance, we could have, instead of X inhibiting phosphorylation of receptors, we could have X activating the dephosphorylation process. So those reactions would look like that. It might be that instead of product X inhibiting phosphorylation, it might be that product X activates or converts into species Y, and it's species Y that has the effect, the inhibiting effect. So in this case we have an extra process, X generates Y, and then Y is the inhibitor. Or possibly X could activate removal of our EPO. So we have process 4 now where EPO degrades or might be captured, but anyway is removed from the system, and that reaction is activated by the presence of X. And if you look at the Wikipedia page at least, it suggests that EPO binds to red blood cells, so after the signalling cascade you expect new red blood cells and they would bind EPO and therefore balance the system in this way. So that could be one way you might look at. So those are remarks. I've now got some exercises. So the first one is describe why the behaviour we observe is negative feedback and try and explain why it's biologically useful in this case. The second thing I'd ask you to do is that in the textbook the modification to the model uses this form where X is generated in the signalling cascade, X then generates Y, and Y is the inhibitor to the phosphorylation of the receptor. So the question I have is, how does that change the behaviour of the system compared to the case where X is the inhibitor? And B, try and with reasons, explain which model you think is best to match the experimental data, so, and why, and maybe what information you might need to decide between the two models, whether it's further experiment or further research in literature. Okay, so the third exercise is that to test the model we've made, it would be possible to run the experiment again, but adding an inhibitor that stops that inhibits the signaling cascade started by the phosphorylated receptors. So we can simulate that by reducing the rate constant at which phosphorylated receptors activate X production. So if you reduce that rate constant by a factor of 10, how does the behavior of the system change? Okay, so that concludes my slides on this topic. What you'll find is the assignment is looking at another situation, changes in blood glucose levels, hopefully using the modelling toolkit and having worked through the EPO signaling cascade example, you'll be able to work through that from the textbook and submit the assignment. So best of luck with that, and I hope this video helped.